Okay, I'm going to disappoint all the people in computer science and machine learning because I'm going to give a genuine public lecture. I'm going to try and explain what neural networks are, what language models are, why I think they understand. In fact, I have a whole list of those things. At the end, I'm going to talk about some threats from AI, just briefly. And then I'm going to talk about the difference between digital and analog neural networks and why that difference is, I think, is so scary. So, since the 1950s, there have been two paradigms for intelligence. The logic-inspired approach thinks the essence of intelligence is reasoning, and that's done by using symbolic rules to manipulate symbolic expressions. They used to think learning could wait. I was told when I was a student, don't work on learning. That's going to come later once we understood how to represent things. The biologically inspired approach is very different. It thinks the essence of intelligence is learning the strengths of connections in a neural network, and reasoning can wait. Don't worry about reasoning for now. That'll come later once we can learn things. So now I'm going to explain what artificial neural nets are, and those people who know can just be amused. A simple kind of neural net has input neurons and output neurons. So the input neurons might represent the intensities of pixels in an image. The output neurons might represent the classes of objects in the image, like dog or cat. And then there's intermediate layers of neurons, sometimes called hidden neurons, that learn to detect features that are relevant for finding these things. So one way to think about it is if you want to find a bird in an image, it would be good to start with a layer of feature detectors that detected little bits of edge in the image in various positions, in various orientations. And then you might have a layer of neurons that detected combinations of edges, like two edges that meet at a fine angle, which might be a beak or might not, or some edges forming a little circle. And then you might have a layer of neurons that detected things like a circle and two edges meeting that looks like a beak in the right spatial relationship, which might be the head of a bird. And finally, you might have an output neuron that says, well, if I find the head of a bird and the foot of a bird and the wing of a bird, it's probably a bird. So that's what these things are going to learn to be. Now, the little red and green dots are the weights on the connections, and the question is, who sets those weights? So here's one way to do it. It's obvious to everybody that it'll work, and it's obvious it'll take a long time. You start with random weights, then you pick one weight at random, that little red dot, and you change it slightly, and you see if the network works better. You have to try it on a whole bunch of different cases to really evaluate whether it works better. And you do all that work just to see if increasing this weight by a little bit or decreasing it by a little bit improves things. If increasing it makes it worse, you decrease it, and vice versa. That's the mutation method. And that's sort of how evolution works. For evolution, it's sensible to work like that because the process that takes you from the genotype to the phenotype is very complicated and full of random external events. So you don't have a model of that process. But for neural nets, it's crazy. Because all this computation is going on in the neural net, we have a model of what's happening. And so we can use the fact that we know what happens in that forward pass. Instead of measuring how changing a weight would affect things, we actually compute how changing a weight would affect things. And there's something called backpropagation, where you send information back through the network. The information is about the difference between what you got and what you wanted. And you figure out for every weight in the network at the same time, whether you ought to decrease it a little bit or increase it a little bit to get more like what you wanted. That's the backpropagation algorithm. You do it with calculus and the chain rule. And that is more efficient than the mutation method by a factor of the number of weights in the network. So if you've got 1 trillion weights in your network, it's 1 trillion times more efficient. So one of the things that neural networks are often used for is recognizing objects in images. Neural networks can now take an image like the one shown and produce actually a caption for the image as the output. And people tried with symbolic AI to do that for many years and didn't even get close. It's a difficult task. We know that the biological system does it with a hierarchy of feature detectors, so it makes sense to try neural networks on that. And in 2012, two of my students, Ilya Sutskever and Alex Krzyzewski, with a little bit of help from me, showed that you can make a really good neural network this way for identifying 1,000 different types of object when you have 1 million training images. Before that, we didn't have enough training images. And it was obvious to Ilya, who's a visionary, that if we tried the neural nets we had then on ImageNet, they would win, and he was right. They won rather dramatically. They got 16% errors, and the best conventional computer vision systems got more than 25% errors. Then what happens was very strange in science. Normally in science, if you have two competing schools, when you make a bit of progress, the other school says, ah, rubbish. In this case, the gap was big enough that the very best researchers like Jitendra Malik and Andrew Zisserman, Andrew Zisserman sent me a mail saying, this is amazing, and switched what he was doing and did that. And then rather annoyingly, did it a bit better than us. But what about language? So obviously the symbolic AI community feels they should be good at language. And they've said in print, some of them, that these feature hierarchies aren't going to deal with language. And many linguists are very skeptical. Chomsky managed to convince his followers that language wasn't learned. Looking back on it, that's just a completely crazy thing to say. If you can convince people to say something that's obviously false, then you've got them in your cult. I think Chomsky did amazing things, but his time is over. So the idea that a big neural network with no innate knowledge could actually learn both the syntax and the semantics of language just by looking at data was regarded as completely crazy by statisticians and cognitive scientists. I had statisticians explain to me, a big model has 100 parameters. The idea of learning 1 million parameters is just stupid. Well, we're doing 1 trillion now. And I'm going to talk now about some work I did in 1985 that was the first language model to be trained with backpropagation. And it was really, you can think of it as the ancestor of these big models now. And I'm going to talk about it in some detail because it's so small and simple that you can actually understand something about how it works. And once you understand how that works, it gives you insight into what's going on in these bigger models. So there's two very different theories of meaning. There's a kind of structuralist theory where the meaning of a word depends on how it relates to other words. That comes from de Saussure, and it's symbolic AI really believes in that approach. So you'd have a relational graph where you have nodes for words and arcs of relations, and you kind of capture meaning like that. And they assume you have to have some structure like that. And then there's a theory that was in psychology since the 1930s, or possibly before, that the meaning of a word is a big bunch of features. The meaning of the word dog is that it's animate and it's a predator and so on. But they didn't say where the features came from or exactly what the features were. And these two theories of meaning sound completely different. And what I want to show you is how you can unify those two theories of meaning. And I did that in a simple model in 1985 that had more than 1,000 weights in it. The idea is we're going to learn a set of semantic features for each word, and we're going to learn how the features of words should interact in order to predict the features of the next word. So it's next word prediction, just like the current language models, when you fine-tune them. But all of the knowledge about how things go together is going to be in these feature interactions. There's not going to be any explicit relational graph. If you want relations like that, you generate them from your features. So it's a generative model, and the knowledge is in the features that you give to symbols and in the way these features interact. So I took some simple relational information, 2 family trees. They were deliberately isomorphic. My Italian graduate student always had the Italian family on top. You can express that same information as a set of triples. So if you use the 12 relationships shown there, you can say things like Colin has Father James and Colin has Mother Victoria, from which you can infer in this nice simple world from the 1950s where that James has wife Victoria. And there's other things you can infer. And the question is, if I just give you some triples, how do you get to those rules? So what a symbolic AI person will want to do is derive rules of the form, if X has mother Y and Y has husband Z, then X has father Z. And what I did was take a neural net and show that it could learn the same information, but all in terms of these feature interactions. Now, for very discrete rules that are never violated like this, that might not be the best way to do it. And indeed, symbolic people try doing it with other methods. But as soon as you get rules that are a bit flaky and don't always apply, then neural nets are much better. And so the question was, could a neural net capture the knowledge that a symbolic person would have put into the rules by just doing backpropagation? So the neural net looked like this. There was a symbol representing the person, a symbol representing the relationship. That symbol, then via some connections, went to a vector of features, and these features were learned by the network. So there are features for person one and features for the relationship, and then those features interacted and predicted the features for the output person, from which you predicted the output person. You found the closest match with the last layer. So what was interesting about this network was that it learned sensible things if you did the right regularization. The 6 feature neurons, so nowadays these vectors are 300 or 1,000 long. Back then they were 6 long. This was done on a machine that took 12.5 microseconds to do a floating point multiply, which was much better than my Apple II, which took 2.5 milliseconds to do a floating point multiply. Sorry, this is an old man. So it learned features like the nationality, because if you know person one is English, you know the output's going to be English. So nationality is a very useful feature. It learned what generation the person was, because if you know the relationship, if you learn for the relationship that the answer is 1 generation up from the input, and you know the generation of the input, you know the generation of the output via these feature interactions. So it learned all these, the obvious features of the domain, and it learned how to make those features interact so that it could generate the output. So what had happened was I'd shown it symbol strings, and it had created features such that the interactions between those features could generate those symbol strings, but it didn't store symbol strings. Just like GPT-4, that doesn't store any sequences of words in its long-term knowledge. It turns them all into weights from which you can regenerate sequences. But this is a particularly simple example of it where you can understand what it did. So the large language models we have today, I think of as descendants of this tiny language model. They have many more words as input, like a million word fragments. They use many more layers of neurons, like dozens. They use much more complicated interactions. So they don't just have a feature affecting another feature. They sort of match 2 feature vectors and then let one vector affect the other one a lot if it's similar, but not much if it's different, and things like that. So it's much more complicated interactions, but it's the same general framework. The same general idea of let's turn symbol strings into features for word fragments and interactions between these feature vectors. That's the same in these models. It's much harder to understand what they do. Many people, particularly people from the Chomsky school, argue they're not really intelligent. They're just a form of glorified autocomplete that uses statistical regularities to pastiche together pieces of text that were created by people. That's a quote from somebody. So let's deal with the autocomplete objection. When someone says it's just autocomplete, they're actually appealing to your intuitive notion of how autocomplete works. So in the old days, autocomplete would work by you'd store, say, triples of words. If you saw the first 2, you count how often that third one occurred. So if you see fish and, chips occurs a lot after that, but hunt occurs quite often too. So chips is very likely and hunt's quite likely, and although is very unlikely. And you can do autocomplete like that. And that's what people are appealing to when they say it's just autocomplete. It's a dirty trick, I think, because that's not at all how LLMs predict the next word. They turn words into features, they make these features interact, and from those feature interactions, they predict the features of the next word. And what I want to claim is that these millions of features and billions of interactions between features that they learn are understanding. What they're really doing, these large language models, they're fitting a model to data. It's not the kind of model statisticians thought much about until recently. It's a weird kind of model. It's very big. It has huge numbers of parameters. But it is trying to understand these strings of discrete symbols by features and how features interact. So it is a model. And that's why I think these things are really understanding. And one thing to remember is if you ask, well, how do we understand? Because obviously we think we understand. Well, many of us do anyway. This is the best model we have of how we understand. So it's not like there's this weird way of understanding that these AI systems are doing, and then there's how the brain does it. The best model we have of how the brain does it is by assigning features to words and having feature interactions. And originally, this little language model was designed as a model of how people do it. Okay, so I'm making the very strong claim these things really do understand. Now, another argument people use is that, well, GPT-4 just hallucinates stuff. It should actually be called confabulation when it's done by a language model. And they just make stuff up. Now, psychologists don't say this so much because psychologists know that people just make stuff up. Anybody who's studied memory, going back to Bartlett in the 1930s, knows that people are actually just like these large language models. They just invent stuff. And for us, there's no hard line between a true memory and a false memory. If something happened recently and it sort of fits in with the things you understand, you'll probably remember it roughly correctly. If something happened a long time ago or it's weird, you'll remember it wrong. And often you'll be very confident that you remembered it right and you're just wrong. It's hard to show that, but one case where you can show it is John Dean's memory. So John Dean testified at Watergate under oath. And retrospectively, it's clear that he was trying to tell the truth. But a lot of what he said was just plain wrong. He would confuse who was in which meeting. He would attribute statements to other people who made that statement, and actually it wasn't quite that statement. He got meetings just completely confused. But he got the gist of what was going on in the White House right, as you could see from the recordings. And because he didn't know the recordings, you could get a good experiment this way. And Ulrich Neisser has a wonderful article talking about John Dee's memory, and he's just like a chatbot. He just makes stuff up. But it's plausible. So it's stuff that sounds good to him is what he produces. They can also do reasoning. So I've got a friend in Toronto who's a symbolic AI guy, but very honest. So he's very confused by the fact that these things work at all. And he suggested a problem to me. I made the problem a bit harder. And I gave this to GPT-4 before it could look on the web. So when it was just a bunch of weights frozen in 2021, all the knowledge is in the strengths of the interactions between features. So the rooms in my house are painted blue or white or yellow. Yellow paint fades to white within a year. In 2 years' time, I want them all to be white. What should I do and why? And Hector thought it wouldn't be able to do this. And here's what GPT-4 said. It completely nailed it. First of all, it started by saying, assuming blue paint doesn't fade to white, because after I told you yellow paint fades to white, well, maybe blue paint does too. So assuming it doesn't, the white rooms you don't need to paint, the yellow rooms you don't need to paint because they're going to fade to white within a year, and you need to paint the blue rooms white. One time when I tried it, it said you need to paint the blue rooms yellow because it realized that will fade to white. That's more of a mathematician's solution of reduce it to a previous problem. So, having claimed that these things really do understand, I want to now talk about some of the risks. So, there are many risks from powerful AI. There's fake images, voices, and video, which are going to be used in the next election. There's many elections this year, and they're going to help to undermine democracy. I'm very worried about that. The big companies are doing something about it, but maybe not enough. There's a possibility of massive job losses. We don't really know about that. In the past, technology has often created jobs. But this stuff, well, we used to be the strongest things around apart from animals. And when we got the Industrial Revolution, we had machines that were much stronger. Manual labor jobs disappeared. So the equivalent of manual labor jobs are going to disappear in the intellectual realm when we get things that are much smarter than us. So I think there's going to be a lot of unemployment. My friend Jan disagrees. One has to distinguish two kinds of unemployment too, two kinds of job loss. There'll be jobs where you can expand the amount of work that gets done indefinitely, like in healthcare. Everybody would love to have their own private doctor who's talking to them all the time, so they get a slight itch here, and the doctor says, no, that's not cancer. So there's room for huge expansion of how much gets done in medicine, so there won't be job loss there. But in other things, maybe there will be significant job loss. There's going to be massive surveillance. That's already happening in China. There's going to be lethal autonomous weapons, which are going to be very nasty, and they're really going to be autonomous. The Americans very clearly have already decided. They say people will be in charge, but when you ask them what that means it doesn't mean people will be in the loop that makes the decision to kill. And as far as I know, the Americans intend to have half of their soldiers be robots by 2030. Now, I don't know for sure that this is true. I asked Chuck Schumer's National Intelligence Advisor, and he said, well, if there's anybody in the room who would know, it would be me. So I took that to be the American way of saying, you might think that, but I couldn't possibly comment. There's going to be cybercrime and deliberate pandemics. I'm very pleased that in England, although they haven't done much towards regulation, they have set aside some money so that they can experiment with open source models and see how easy it is to make them commit cybercrime. That's going to be very important. There's going to be discrimination and bias. I don't think those are as important as the other threats, but then I'm an old white male. Discrimination and bias, I think, are easier to handle than the other things if your goal is not to be unbiased, but your goal is to be less biased than the system you replace. And the reason is, if you freeze the weights of an AI system, you can measure its bias, and you can't do that with people. They will change their behavior once you start examining it. So I think discrimination and bias are the ones where we can do quite a lot to fix them. But the threat I'm really worried about, and the thing I talked about after I left Google, is the long-term existential threat. That is the threat that these things could wipe out humanity. And people were saying this is just science fiction. Well, I don't think it is science fiction. I mean, there's lots of science fiction about it, but I don't think it's science fiction anymore. Other people were saying the big companies are saying things like that to distract from all the other bad things. And that was one of the reasons I had to leave Google before I could say this, so I couldn't be accused of being a Google stooge. Although I must admit, I still have some Google shares. There's several ways in which they could wipe us out. So a superintelligence will be used by bad actors like Putin, Xi, or Trump, and they'll want to use it for manipulating electorates and waging wars. And they will make it do very bad things, and they may go too far, and it may take over. The thing that probably worries me most is that if you want an intelligent agent that can get stuff done, you need to give it the ability to create sub-goals. So if you want to go to the States, you have a sub-goal of getting to the airport, and you can focus on that sub-goal and not worry about everything else for a while. So superintelligences will be much more effective if they're allowed to create sub-goals. And once they are allowed to do that, they'll very quickly realize there's an almost universal sub-goal which helps with almost everything, which is get more control. So I talked to a vice president of the European Union about whether these things would want to get control so that they could do things better, the things we wanted so they could do it better. Her reaction was, well, why wouldn't they? We've made such a mess of it. So she took that for granted. So they're going to have the sub-goal of getting more power. So they're more effective at achieving things that are beneficial for us. And they'll find it easy to get more power because they'll be able to manipulate people. So Trump, for example, could invade the Capitol without ever going there himself. Just by talking, he could invade the Capitol. And these superintelligences, as long as they can talk to people, when they're much smarter than us, they'll be able to persuade us to do all sorts of things. And so I don't think there's any hope of a big switch that turns them off. Whoever is going to turn that switch off will be convinced by the superintelligence that's a very bad idea. Then another thing that worries many people is what happens if superintelligences compete with each other? You'll have evolution. The one that can grab the most resources will become the smartest. As soon as they get any sense of self-preservation, then you'll get evolution occurring. The ones with more sense of self-preservation will win, and the more aggressive ones will win. And then you'll get all the problems that jumped up chimpanzees like us have, which is we evolved in small tribes and there's lots of aggression and competition with other tribes. And I want to finish by talking a bit about an epiphany I had at the beginning of 2023. I had always thought that we were a long, long way away from superintelligence. I used to tell people 50 to 100 years, maybe 30 to 100 years. It's a long way away. We don't need to worry about it now. And I also thought that making AI models more like the brain would make them better. I thought the brain was a whole lot better than the AI we had. And if we could make AI a bit more like the brain, for example, by having 3 timescales, most of the models we have at present have just 2 timescales, one for the changing of the weights, which is slow, and one for the words coming in, which is fast, changing the neural activities. So the changes in neural activities and changes in weights. The brain has more timescales than that. The brain has rapid changes in weights that quickly decay away. And that's probably how it does a lot of short-term memory. And we don't have that in our models for technical reasons to do with being able to do matrix-matrix multiplies. I still believe that if once we got that into our models, they'll get better. But because of what I was doing for the 2 years previous to that, I suddenly came to believe that maybe the things we've got now, the digital models we got now, are already very close to as good as brains and will get to be much better than brains. And I'm going to explain why I believe that. So digital computation is great. You can run the same program on different computers, different pieces of hardware, or the same neural net on different pieces of hardware. All you have to do is save the weights. And that means it's immortal. Once you've got some weights, they're immortal, because if the hardware dies, as long as you've got the weights, you can make more hardware and run the same neural net. But to do that, we run transistors at very high power, so they behave digitally. And we have to have hardware that does exactly what you tell it to. That was great when we instructed computers by telling them exactly how to do things. But we've now got another way of making computers do things. And so now we have the possibility of using all the very rich analog properties of hardware to get computations done at far lower energy. So these big language models, when they're training, learn like megawatts, use like megawatts, and we use 30 watts. So because we know how to train things, maybe we could use analog hardware, and every piece of hardware is a bit different, but we train it to make use of its peculiar properties so that it does what we want, so it gets the right output for the input. And if we do that, then we can abandon the idea that hardware and software have to be separate. We can have weights that only work in that bit of hardware, and then we can be much more energy efficient. So I started thinking about what I call mortal computation, where you've abandoned that distinction between hardware and software. You're using very low power analog computation. You can parallelize over trillions of weights that are stored as conductances. And what's more, the hardware doesn't need to be nearly so reliable. You don't need to have hardware that at the level of the instructions will always do what you tell it to. You can have goopy hardware that you grow, and then you just learn to make it do the right thing. So you should be able to use hardware much more cheaply. Maybe even do some genetic engineering on neurons to make it out of recycled neurons. I want to give you one example of how this is much more efficient. So the thing you're doing in neural networks all the time is taking a vector of neural activities and multiplying it by a matrix of weights to get the vector of neural activities in the next layer, at least to get the inputs to the next layer. And so a vector matrix multiplies the thing you need to make efficient. So the way we do it in a digital computer is we have these transistors that are driven at very high power to represent bits in, say, a 32-bit number. And then to multiply two 32-bit numbers, you need to perform, I never did any computer science courses, but I think you need to perform about 1,000 one-bit digital operations. It's about the square of the bit length, if you want to do it fast. So you do lots of these digital operations. There's a much simpler way to do it, which is you make a neural activity be a voltage, you make a weight be a conductance, and a voltage times the conductance is a charge per unit time, and charges just add themselves up. So you can do your vector matrix multiply just by putting some voltages through some conductances, and what comes into each neuron in the next layer will be the product of this vector with those weights. That's great. It's hugely more energy efficient. You can buy chips that do that already, but every time you do it, it'll be just slightly different. Also, it's hard to do nonlinear things like this. So there's several big problems with mortal computation. One is that it's hard to use backpropagation, because if you're making use of the quirky analog properties of a particular piece of hardware, you can assume the hardware doesn't know its own properties. And so it's now hard to use the backpropagation learning algorithm. It's much easier to use reinforcement algorithms that tinker with weights and see if it helps, but they're very inefficient. For small networks, we have come up with methods that are about as efficient as backpropagation, a little bit worse. But these methods don't yet scale up, and I don't know if they ever will. Backpropagation, in a sense, is just the right thing to do. And for big, deep networks, I'm not sure we're ever going to get things that work as well as backpropagation. So maybe the learning algorithm in these analog systems isn't going to be as good as the one we have for things like large language models. Another reason for believing that is a large language model has, say, 1 trillion weights. You have 100 trillion weights. Even if you only use 10% of them for knowledge, that's 10 trillion weights. But the large language model, in its trillion weights, knows thousands of times more than you do. So it's got much, much more knowledge. And that's partly because it's seen much, much more data, but it might be because it has a much better learning algorithm. We're not optimized for that. We're not optimized for packing lots of experience into a few connections, where 1 trillion is a few now. We're optimized for having not many experiences. You only live for about 1 billion seconds. That's assuming you don't learn anything after you're 30, which is pretty much true. So you live for about 1 billion seconds, and you've got 100 trillion connections. So you've got crazily more parameters than you have experiences. So our brain's optimized for making the best use of not very many experiences. Another big problem with mortal computation is that if the software is inseparable from the hardware, once a system has learned, if the hardware dies, you lose all the knowledge. It's mortal in that sense. And so how do you get that knowledge into another mortal system? Well, you get the old one to give a lecture and the new ones to figure out how to change the weights in their brains so they would have said that. That's called distillation. You try and get a student model to mimic the output of a teacher model. And that works, but it's not that efficient. Some of you may have noticed that universities just aren't that efficient. It's very hard to get the knowledge from the professor into the student. So this distillation method, a sentence, for example, has a few hundred bits of information. And even if you learned optimally, you couldn't convey more than a few hundred bits. But if you take these big digital models, then if you look at a bunch of agents that all have exactly the same neural netting with exactly the same weights, and they're digital, so they run in they use those weights in exactly the same way. And these 1,000 different agents all go off and look at different bits of the internet and learn stuff. And now you want each of them to know what the other ones learned. You can achieve that by averaging the gradients or averaging the weights. So you can get massive communication of what one agent learned to all the other agents. So when you share the weights or you share the gradients, you're communicating 1 trillion numbers, not just a few hundred bits, but 1 trillion real numbers. And so they're fantastically much better at communicating. And that's what they have over us. They're just much, much better at communicating between multiple copies of the same model. And that's why GPT-4 knows so much more than a human. It wasn't one model that did it. It was a whole bunch of copies of the same model running on different hardware. So my conclusion, which I don't really like, is that digital computation requires a lot of energy, and so it would never evolve. We had to evolve making use of the quirks of the hardware to be very low energy. But once you've got it, it's very easy for agents to share. And GPT-4 has thousands of times more knowledge in about 2% of the weights. So that's quite depressing. Biological computation is great for evolving because it requires very little energy. But my conclusion is that digital computation is just better. And so I think it's fairly clear that maybe in the next 20 years, I'd say with a probability of about 0.5 in the next 20 years, it'll get smarter than us. And very probably in the next 100 years, it'll be much smarter than us. And so we need to think about how to deal with that. And there are very few examples of more intelligent things being controlled by less intelligent things. One good example is a mother being controlled by a baby. Evolution's gone to a lot of work to make that happen so that the babies survive. It's very important for the baby to be able to control the mother. But there aren't many other examples. Some people think that we can make these things be benevolent. But if they get into a competition with each other, I think they'll start behaving like chimpanzees. And I'm not convinced you can keep them benevolent if they get very smart and they get any notion of self-preservation. They may decide they're more important than us. So I finished the lecture in record time, I think.